As we discussed in the lecture of latch, I mentioned that the latch is level sensitive. So, as long as the signal level is active, the latch follows the input and changes the output according to the change in the input. Uh, but we need to have a storage element that can change their state no more than once per one clock cycle. And if you remember, I mentioned that a flip-flop is built for this purpose. The flip-flop changes one time per clock cycle. So the output of a flip-flop can change only one time per clock cycle. And so latch is level sensitive, and if this is the clock cycle, if the inputs applied to the latch change during the clock pulse is still at the logic 1, at these logics, the latch will respond to the new values and the new output state may occur. So as long as the clock is active, changing the input may change the output. Okay, so since the state of this latch may keep changing for as long as the clock pulse is active, we may have different outputs in one clock cycle. Hence, we need a storage element that can change their states no more than once during one clock cycle. So flip-flop, which is flip-flop, which is edge sensitive, are constructed, these flip-flops are constructed to make like them operate properly when they are at the part of the sequential circuit. So they can change only one per clock cycle, not more than one time per clock cycle. So we have like positive edge triggered flip-flop and negative edge triggered flip-flop. So for positive edge triggered, the flip-flop change its state at positive transitions, one per clock cycle. And in negative edge triggered flip-flops, the flip-flop change its state maximum of once per clock cycle at the falling edge. Okay, so we want to build and construct flip-flop. We know the main difference. Latch changes its state as long as the clock is active, but flip-flop changes its output only one time per clock cycle. Okay, so the first flip-flop that we will learn today is edge triggered D flip-flop. Edge triggered D flip-flop. And this one is the circuit for this flip-flop. If you remember, I said that the latch is the basic component to build flip-flops. So here I'm showing that we build the flip-flop using two latches. And this flip-flop is called master slave flip-flop. Okay, so we have the latch which has D input, enable input. The second D latch has D input, enable input, Q and Q bar outputs. The first latch we call it master. The second latch we call it slave, not level, slave. And we connect the output of master to the input of the slave. Okay, and we call it Q sub M. The output of slave, we call it Q of S. The input of master is connected to the data input. And also we have a clock input which is connected to the enable of master, and then we complement this clock cycle and we connect it to the enable of slave. Of course, this Q, we have another output in the slave, and this one is the general configuration of master slave flip-flop. The flip-flop, let's see how does it work. So we put all these devices in single block and we call it master slave D flip-flop. Okay, this one is the master slave D flip-flop. But how does this master slave D flip-flop work? The first thing we should know is the first stage, which we call it master, the first stage, which is master, changes its state while clock is 1. Look here, we see that as long as the clock is 1, the enable is active, so master changes its input. It's like a state as long as clock is 1, but when the clock is 1, we see that the enable of the slave is deactivated. So also we can say the second stage, which we call it slave, changes its state while clock is equal to 0. Okay, the operation of the circuit is such that when the clock is high, let's have the clock here, let's say this one is a clock. Okay, so this one is clock. While the clock is high, the master tracks the value of the D input signal and a slave does not change. So as long as clock is high, master is on, tracks the value of the D input. D input like moves from the input to the QM. Okay, as long as the clock is active, while the slave does not change because the slave is off. So as a result, the value of QM, the value of while the clock is active at this time, the value of QM follows any changes in D. And the value of QS remains constant. Why value of QS remains constant? Because a slave is off. Why the value of QM why the value of QM follows any change in D? Because master is on. So as long as the clock is active, the QM is same as D, follows the D, but QS is constant. When the clock signal changes to 0, okay, so now let's say the clock signal changed to the 0, the green highlight area. When the clock cycle, let me just erase this highlights. Okay, when the clock signal changes to 0, the master stage stops following the changes, because at this area, as soon as we see as soon as it sees like the falling edge, as soon as it sees the falling edge, the master will be deactivated, and it stops following the changes in the input. At the same time, at the same time, the slave stage respond to the value of the signal QM. Why? Because at the same, oh no, so let me just fix it. Okay, let me just erase this. Okay, let me just explain one more time. I said when the clock change to the 0, the master stage stops following the changes in the D input. At the same time, the slave turns on and respond to the value of the signals of QM, because QM is the input of a slave. Since QM does not change, since the QM does not change while clock is 0. Why it does not change? Because while clock is 0, master is off, and QM does not change. So we can say, since QM does not change while clock is 0, the slave stage can undergo at most one change of state during a clock cycle. One change of a state during a clock cycle. So one more time, let me explain one more time. Say I said that as long as we are in the yellow highlighted area, QM follows D, but QS is constant because a slave is off. At the transition moment, which I showed with like a red arrow, at this transition moment, the last value of D, which transferred to QM, will be like remains at the output of master, and after this transition, the master will turn off, and the QM will be constant. What is the value of the QM during this half a cycle? The value of QM at this half a cycle is the last value of D, before transition. The last value of D before the transition. So the last value of D will be moved to the QM at the transition. After the transition occurs, in the green highlighted area, the master is off. So QM does not change. Okay, does not change. What is the value? The last value of D before the transition. Okay, so in the green highlighted area, QM does not change, but QS follows the QM. And as the QM is constant, of course, QS is also constant. So this one is like the QS will be remain constant until the next falling edge, because in the next activated area, a slave is off, master is on, and so on. In the next one, master is on and a slave, master is off and a slave is on. So let me just write it down. So at here, so master on, slave off. Here master off, slave on. Here master on, slave off. Okay, and at these falling edges, these falling edges, the state of flip-flop changes. Okay, at these falling edges, the state of flip-flop changes, and the maximum number of changes, as we see here, is 1 time per clock cycle. Okay, so this one is a master-slave D flip-flop, and how does it work? By the way, if we look to this circuit, we see that this flip-flop is falling edge sensitive. Falling edge sensitive. If we look, we see that at falling edges, the value of the flip-flop updated. If we want to have rising edge sensitive flip-flop, rising edge sensitive, or let's call it positive edge triggered flip-flop, what we need to do, we need to flip the clock. How we can do that? We need to add another another inverter here. So if we add another inverter here, so this flip-flop will be positive edge sensitive. So if we have no inverter here and we have this circuit is negative edge sensitive. Negative edge. In order to make it positive edge, as I said, we need to add like an inverter at this location to change it to positive edge sensitive. Okay, so this one is how a flip-flop how does a flip-flop work, and I want to compare some flip-flops and latches. Before moving to the next part, let me show you the characteristic table of D flip-flop. Characteristic table of D flip-flop. So characteristic table. Okay, we say we have D and we have Q of T plus 1. If D is 0, QT plus 1 is 0, which is a reset. If D is 1, QT plus 1 is 1, which is called set. We can just show this characteristic table in a form of equation. We can say Q of T plus 1 is equal to D. You see, Q T plus 1 is equal to D. Okay, this one is the characteristic table or equation of D flip-flop. And what is the symbol of D flip-flop? If you remember, for the latch, D latch, I said that we show a D latch in this form: input D, enable Q and Q bar. This one is positive level sensitive latch. Positive level means that as long as enable is 1, we can connect enable to the clock. As long as enable or clock is 1, the latch follows the changes. If we want to have a negative level sensitive or low level sensitive, not a positive level, let's call it high level sensitive, it's better. High level sensitive. High level sensitive. If we want to have a low level sensitive latch, we keep our D, Q, Q bar, and if you remember, I said that like a small circle means in not. So we have like a small circle, and this one is low level sensitive latch. So this small circle means not gate. Not gate, not in fact, just inverts. Okay, so this one is a low level sensitive latch, and this one is high level sensitive latch. What about flip-flop? By the way, we know that these two latches are level sensitives, but for flip-flop, we say we have D input, Q output, Q bar output, and here is the clock. If we call it clock or enable, let's call it clock, yeah, because it's edge sensitive. If we call it clock, how do we know this one is flip-flop, not latch? There is a difference in the way we show the flip-flop. We use one small triangle here in the clock input, and it like represents this figure as a flip-flop. So this one like shows that this schematic is for a flip-flop, not for a latch. So this one is active positive edge, flip-flop, or I can call it positive edge triggered, positive edge sensitive, rising edge sensitive. Okay, so different names, but all of them have the same meaning. And for like negative edge or falling edge, for the active negative edge flip-flop, we have Q, we have Q bar, we have D. So we have this triangle to identify it as flip-flop, and this small circle to identify it as negative edge sensitive. So this one is the representation of this. So it's very important that you learn these four figures. Okay, it's very important. So whenever you see these figures, you should immediately recognize what kind of memory element is this device. Okay, now I want to compare different, just like flip-flop and latch in an example. So let's call it comparison of level sensitive versus edge triggered D storage elements. Okay, so let's assume we have three elements. Okay, all of them have input D. These input Ds are connected to each other, and connected to D. It has output Q and Q bar. For the first one, we call it QA and QA bar. The second one has also Q and Q bar, which we call it QB and QB bar. The third one, the same. We call it QC, QC bar. And all of them have clock, and the clock is connected to these elements. This clock, and the second one has this triangle. The third one has both triangle and circle. So if we want to identify these three storage elements, definitely we know that this one is mm, high level sensitive latch, D-latch. This one is positive edge sensitive D flip-flop, and of course this one is negative edge sensitive D flip-flop. Okay, so we have these three D flops, and we apply an input, and we want to see the outputs. So there is a way to show the response of the storage elements like to the inputs, which is called timing diagram. Timing diagram. Okay, in the timing diagram, we show the clock. Okay, some dashed lines to to have exact location or exact time of transition. In timing diagram, we have clock, we have input, and we are supposed to find output. So QA, QB, and QC. So we have clock, we have input. Let's see what is the input. So by the way, let me just finish it first. So this one is input. Okay, this one is the input, and we want to find the output. So this graph is like at this region, the value of D is 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0. Okay, so this one is the values, and we want to find QA. What is A? Let's go back to A. A is high level sensitive D-latch. High level sensitive D-latch, I said that as long as the clock cycle is high, the output follows the input. So we start from 0. We start from 0, and as we reach to active area, which is high level of the clock, the output follows the input. So these inputs will be exactly copy paste here because the output follows the input. So we can say the output will be 0, 1. You see, during this level, the output changes several times. And if you remember, I said the latch changes its output during the active clock cycle, and we don't want to have these changes in synchronized circuits, and so it's the reason we try to have another storage element which is edge sensitive, and we call it flip-flop. So when the latch reaches to the transition and it starts to experience the deactivated area of uh, clock cycle, the last value of the input, which is 0, will be remain on the output and doesn't change. So the last value of the input will be remains on the output until the next active level. On the next active level, which is here, the output starts to follow the input. So input here is 0, so output is 0 and follows the input and up to this point. Up to this point, and at this point, the last value of the input will be remain on the output, and output is 1. So this one is the latch. Okay, you see how the output changes. QB. What is QB? Let's see. QB is positive edge sensitive D flip-flop. Positive edge sensitive D flip-flop says that the output can be changed only once at the rising edge. At which edges? At this edge and this edge. Okay, so start from 0, QB. At this edge, what is the input will move to the output. So what is the input of the flip-flop at transition? Of course is 1. So the output will be changed to 1. And despite the latch, this output will be remain constant until the next rising edge. Where is the next rising edge? Is here. So until the next rising edge, the output is constant. No matter what changes are happening on the input, the output is constant. At the second next rising edge, the flip-flop looks to the input and transfers it to the output. So it's 0, the output changes to 0. And this one is the timing diagram for positive edge trigger D flip-flop. Let's move to negative edge trigger D flip-flop. Negative edge trigger D flip-flop changes at falling edges. So we start from 0. At this rising edge, nothing changes because it's a rising edge. At this falling edge, which is the first falling edge, the input, which is 0, will be transferred to the output, which is 0. So we still have 0 until the next falling edge. On the next falling edge, again, the value of the input at the transition point will be moved to the output, because it's 1, the flip-flop will set to 1. So this one is how does a flip-flop work? D flip-flop. Okay, in the next lecture, I will talk about the different other types of the flip-flop.